Hey there! So, the screen you're watching this on right now, it's painting a picture with millions, and I mean millions, of different colors. But have you ever actually stopped to wonder how it's doing that? Well, in this explainer, we're going to peel back the layers on the one component that makes it all possible. It's an incredible piece of invisible engineering called the color filter.
I mean, really think about it. Every photo, every video, every single shade and gradient you see is being mixed, right now, in real time, from just three basic colors: red, green, and blue. So how in the world does your display pull off this incredible trick of the light so perfectly?
You know, the answer lies in what I'd call the unsung hero of every LCD panel, the color filter. It's kind of funny. Before this thing came along, liquid crystal displays were just, well, they were black and white. Think of an old calculator screen. The color filter is the magic ingredient that transforms that simple on or off display into the vibrant, full-color window you're looking through right now.
So how does it all work? Well, to figure that out, we need to zoom in. No, I mean way in, down to the level of a single pixel, and see how this thing is built, layer by microscopic layer.
Right, so every single pixel you see is actually made of three even smaller parts. We call them subpixels. You've got one for red, one for green, and one for blue. Each of these subpixels basically acts like a tiny specialized stained glass window. The red one, it only lets red light through. The green only lets green through, and you guessed it, the blue only lets blue through. By controlling exactly how much light shines through each of these three little windows, your screen can mix them together to create pretty much any color you can imagine.
Okay, but this design immediately creates a huge engineering problem. When you pack these tiny color cells so close together, light can just spill from one to the next. That makes the colors look muddy, blurry, just a mess. The solution is actually super elegant. It's called a black matrix. The best way to think of it is like the dark grout between tiles in a mosaic. This black grid perfectly isolates every red, green, and blue cell, stopping any color from bleeding over, which dramatically boosts the sharpness and contrast of the whole image.
Now, for this black matrix to do its job, it has to be incredibly good at blocking light. Its performance is measured by something called optical density, or OD. And for any high-quality display, you're looking for an OD that's greater than 3.5.
So, what on earth does that number even mean? Well, optical density is just a way of measuring how much light a material can absorb. For perspective, an OD of 3 means the material is blocking 99.9% of the light. Only a tiny 1,000th of the light gets to pass through. So an OD of 3.5 is even better, and it's what ensures the blocks on your screen are truly black and the colors are perfectly pure.
All right, so the RGB cells in the black matrix are the stars of the show, but they're only part of the story. There are these other critical, totally invisible layers that make sure the whole microscopic structure works just right.
First up, there's the overcoat. See, the process of putting down the color filters creates a bumpy, uneven surface. That's a big problem because it would distort the image. So the overcoat is just a clear acrylic layer that smooths everything out into a perfectly flat plane. It also acts like a protective shield. Then you have these things called column spacers. They're basically microscopic pillars, only about 4 micrometers high, and their only job is to maintain a perfectly consistent gap between the color filter and the glass below it. That tiny gap is where the liquid crystal lives, and it has to be exact for the display to work at all.
So we've built the physical pixel, but this kind of brings up a more philosophical question. How do we make sure that the red that my screen makes is the exact same red that your screen is making, maybe on the other side of the world?
And this is a huge deal, right? For everything from online shopping to movies to work, we need a universal, mathematical way to define color. How do you take something as subjective as seeing the color red and turn it into cold, hard data that everyone can agree on?
The answer is a concept called color gamut. The easiest way to picture it is to imagine a chart that contains every single color the human eye can possibly see. It kind of looks like a colorful horseshoe. The color gamut of your display is shown as a triangle inside that chart. The 3 points of the triangle are the purest red, green, and blue your screen can possibly make. Any color inside that triangle is a color your display can show. So it's simple. A bigger triangle means a wider range of more vibrant colors.
And that's exactly why we have different color standards, with each one designed for a specific job. For instance, sRGB is the standard for pretty much everything you see on the internet and on your HD TV. But a professional photographer, they might work in something called Adobe RGB, which has a larger triangle, especially in the greens, so it can better match what a fancy printer can produce. And then you have digital cinema, or DCI, which pushes that range even further to get those incredibly rich colors you expect to see at the movie theater.
Okay, so now we get the structure and the science. So let's just touch on how these incredible filters are actually made and what kind of cool innovations are pushing the technology forward. So each layer, the black matrix, then the red cells, then the green, then the blue, is patterned using a crazy process called photolithography. First, a light-sensitive material gets spread onto the glass. Then, UV light is shone through a patterned mask, which acts kind of like a super high-tech stencil. The light hardens the material in a very specific shape, and then a chemical wash comes in and just removes all the unhardened stuff. This whole process is then repeated for every single layer to build up the entire complex structure with mind-boggling precision.
But, engineers, they're never satisfied. The standard RGB setup has a basic weakness. At best, only about a third of the light from the backlight ever makes it through the filter to your eyes. So they started asking, what if we could do better?
And this thinking led to innovations like RGBW technology. The idea is so simple, but it's brilliant. They just add a fourth clear subpixel to the mix, a white one. This clear cell is like an open window. It just lets the full backlight shine through totally unfiltered. What's the result? Well, the screen can either get way brighter, which is awesome for using your phone outside, or it can produce the same brightness while using a lot less power. It's just a really clever hack on the original design that makes your battery last longer.
The color filter is just a perfect example of the absolutely astounding complexity hidden inside the devices we use every single day without even thinking about it. It really makes you wonder, what other objects in your life right now are hiding a similar level of invisible and totally brilliant engineering? Thanks for joining me on this one.